Everyone. Welcome to the first episode of a series of lectures I'm going to be doing on quantum mechanics and electronic structure. Today I sort of want to introduce some maths behind what we're going to do and then finish by deriving the Schrodinger equation and secular equation, which we're going to be solving throughout the rest of the series. Um, so to begin with, we're going to say that the state of our quantum mechanical system can be described by some vector psi and some set h. And h is going to form a Hilbert space, which is going to be a set which has the vector field operations defined on it. So that's vector addition, scalar multiplication, and then also we're going to have some inner products defined. And so throughout this first bit, I'm sort of going to be referring to r squared as sort of a simple vector field that you're probably a bit more familiar with, but we want to generalize the things we can do to it to a vector field which has both complex numbers in it and also a field which may have infinite length vectors in it. And so let's say that A is equal to 1, 2, and B is equal to 3, 4. We can add these together, and we can get 4, 6, which is also going to be in r squared. And we can also multiply A by a scalar, say 2A is equal to 2, 4, and that's another vector. So we can do the same thing with vectors in our Hilbert space, and so we can say that psi plus phi is going to be another vector, and then if I take some number alpha and I multiply it by psi, I can get another element of my Hilbert space. So my addition is taking in h squared and it is mapping it to h, and my scalar multiplication is taking a complex number and a vector and mapping it to a vector. So the analog to my inner product is going to be the dot product, and so if I take A dot B, what I'm doing is I'm looking at each of the dimensions in it. So here I just have 2, and I'm multiplying across, so AN, BN. Alternatively, I can define A dot B to be the transpose of A times B, which we'll use a bit more of later. So anyways, the first property with this dot product is it commutes, so A dot B is equal to B dot A, and while this is true for a real, the dot product in the reals, this generalized inner product, which might take complex numbers, is not always going to have this being the case. And so, first of all, let's just define our inner product. It's going to take in 2 vectors, and it's going to spit out a complex number instead. So, because of course A dot B is spitting out a real number here, which is going to be 11 in this case. And so while the dot product commutes, my generalized inner product is going to be anti-commutative, and so if I swap the order around, I'm going to take the complex conjugate, which I'm going to write as a bar on top of my number. The dot product is also linear, so let's introduce C as 5, 6, right? A dot B plus C is equal to A dot B plus A dot C, and so it is true that if I take the inner product of phi and alpha psi 1 plus beta psi 2, I can split this up into alpha times my first inner product plus beta times the second one. And combining these two properties together, the first slot isn't actually going to be linear, and so instead, if I've got alpha psi 1 plus beta, alpha phi 1 plus beta phi 2, I'm going to pull out an alpha bar and a beta bar instead. Another thing which is useful to have about a vector is length. So we can say that the norm of A is equal to sort of a Euclidean distance it travels, and so that's the sum of an squared, and that is equal to a dot a, and so I'm square rooting that. And so similarly, in R space, we can define the norm of psi to be the square root of the inner product of psi with itself, and this function is going to map from H onto the reals, because of course our length needs to be real, and even better than that, our length is going to be greater than or equal to 0. And it's only equal to 0 if psi is 0. Right, there's no other way I can get a length of 0. And so, of course, if that's the case, and I've got a real length, then that means if I square it, I'm also going to have a positive real number. If I've got a positive real length and I square it, that also means that the inner product of psi with itself is always greater than or equal to 0 and is real. Yeah, so that's the basics of arithmetic with inner products. And I guess we should go about defining a useful one. And say, so for that, we're going to need a basis set. So similarly to how for in R squared, we sort of iterated over our basis of the x and then the y, we're going to need something similar. And so for a basis set, which I'm going to call Cn, I'm going to define, first of all, the orthonormality condition for this. So the first part is the normalization of my vectors, and that means that Cn dot Cn is equal to 1, and so the length of Cn is 1. And so in R squared, the orthonormal basis you're probably going to be using is I hat and j hat, so 1, 0, and 0, 1, and these have a length of 1. However, if I dot instead Cn and Cm, I'm going to get 0 if I pick different ones. So if you dot these together, you're going to get 0. And so a nice way to write this is Cm dot Cn is going to be equal to delta Mn, where delta Mn is the Kronecker delta function, which is going to return 1 if M and N are equal, otherwise 0. So we're going to introduce a new notation now, which is Dirac notation. And so a vector psi is going to be written with these brackets, and it's going to be called a ket vector. This is a ket. It's still an H. And if I write something like this is going to be called a bra vector. And instead, this is going to act as a linear functional, and it's going to be a mapping from H onto C. So essentially, I can apply this to do my inner product, right? So what I'm saying is this is equal to the inner product of phi and psi, right? Which is going to return me a complex number. So I'm essentially applying this to this. Anyways, so for basis decomposition in R squared, we can say that our vector A, which was 1, 2, is equal to 1 lot of I hat plus 2 lots of j hat. And to get this 1, we can write that as 1, 2 dotted with 1, 0, right? And similarly, this 2 can be gotten by doing 1, 2 dotted with 0, 1. And so A can be written as the sum of A dot Cn multiplied by Cn for each n in my basis set length. And so similarly, psi can be written as the sum. My basis set, instead of being Cm, is going to be a set of my ket vectors, which are n. And so I'm going to apply the bra n onto psi to get the projection of psi in that direction, and then I'm going to multiply it by moving stuff around. I can write this like this. And then as psi doesn't actually depend on n, I can take it outside of my sum, right? So it's equal to psi multiplied by the sum. And if this is equal to psi, therefore this, speaking in the language of vectors, is the identity matrix, but I'm just going to say it as an identity operation. And essentially what's happening here is instead of multiplying a bra by a ket, so going bra then ket, I'm going ket then bra. So this is the equivalent of instead of going a, t, b, I'm now going a, b, t. So instead of my dimensions for my multiplication being 1 by 2, and then 2 by 1, right, which is going to give me a 1 by 1, I'm now going to be doing a 2 by 1 by a 1 by 2, and so my output is going to be a 2 by 2 matrix. And so summing all of these matrices up for each of my bases is going to end up giving me the identity matrix in total. However, of course, as I mentioned earlier, psi is often infinite, and so the sigma notation isn't the most accurate, and instead I'm going to express it as the continuous version, the integral of x psi dx. So I'm going over all the different values of x I can have in some domain omega, and I'm essentially getting the basis vector for each of these, extracting the information that psi has to say about x, and then multiplying it by the basis x to get my total wave function, or my total ket vector. And so similarly, I can write one of these completeness relationships. So I is equal to the integral of this outer product of x's. But also, what's quite convenient is if I write this, so this is the information that psi has to say about x as psi of x. I've now essentially translated my infinite vector into a function, which is a bit more useful and a bit more meaningful. But anyways, we can now derive a formula that's useful for our inner product. So if we had phi and psi, what we can do is insert in the identity into this inner product, because of course I times psi is going to do nothing to it. It's going to map my Hilbert space onto my Hilbert space. And it's going to keep everything the same, right? So I can get rid of this, and then I'm applying my bra to that. So that's going to map H onto C. But anyways, I now have a formula for I, and so if I write the integral, and now I can see some familiar things. So this we said was psi of x, and this we're going to use the first relationship we looked at, which is the anti-commutativity, and write this. Swap them around and take the conjugate. And so this is equal to the conjugate of phi of x. And as such, the inner product of phi and psi is equal to the integral of the conjugate of phi of x times psi of x dx over some domain omega. Great. This is all a bit abstract, and so the first thing I'm going to introduce is the Born interpretation. So this function psi of x, if I take the modulus of it and square it, it is going to give me the probability density that I will find a particle at a position x. And so if I were to take the integral of all of my probabilities, we expect that to be 1, right? The total probabilities are 1. But anyways, if I take the modulus of a complex number squared, I can write this as its conjugate times space form, and so writing this, to get phi bar of x, phi of x, sorry, psi bar, and psi of x dx. And now I can write this as the inner product of psi and psi. This is the length of psi, and this is also the modulus of, not the modulus, the norm of psi squared. Anyways, all of these are equal to 1 using this interpretation. Great. Anyways, say we want to measure something about a quantum system. We are going to say that there is an operator A, and that when we apply it to psi, is going to tell us something about the system. We'll go into some examples later when we look at position and momentum and energy and such. Anyways, A is going to act like a linear transformation. This is equivalent to applying a matrix to a vector. So it is going to map its domain onto another vector. The domain is of course a subset of the Hilbert space. It might not be able to take in every vector. And A is a linear transformation. So if I apply it to alpha phi plus beta psi, where alpha and beta are scalars, then I can bring them out. And so this is going to be equal to alpha A phi plus beta A psi. I would like to also introduce the adjoint here. So similarly, as to when I inserted the identity into my inner product, I'm able to insert other linear transformations and matrices into my inner product. And so if I have an inner product, which is like this, this is again equal to applying A to psi, which produces another vector, and then applying the bra phi to this new vector to get a complex number out. So I'm going to write the result of the first operation as just A psi inside one cat vector, and this is like this. However, this is also equivalent to sort of applying an overall operation to psi, which converts psi to a complex number straight away, and so that is going to take the form of a cat vector, and I'm going to call that A cross phi, which I'm going to apply to psi. And A cross here is what I call the adjoint of A. And for a vast majority of the operations I'm going to deal with in quantum mechanics, it's going to turn out that A and A bar and A cross are the same thing. And so I call this type of operation self-adjoint. And so for the case of a matrix, it turns out that the adjoint of A is going to be equal to the transpose of A, and then I've conjugated every element in it. So that is the element at row I in column J in A cross is going to be equal to the element at row J in column I in A conjugated. Great. So anyways, one thing I can do is consider the equation A of psi is equal to little a of psi. And so essentially we said that A is an operation which represents measuring something. And so if the system is in a state where psi ends up satisfying this equation, then we call this state an eigenstate. A here is what we call an eigenvalue. And if this is the case, when I do my measurement, I'm always going to get a result of A, of little a. If that's not the case, I'm instead going to look at the expected value. And I'm going to say that the expected value of A, which I'm going to write like this, is going to be equal to the integral of of psi bar of x multiplied by a psi of x dx, which, if you recall, was psi a psi. If the probabilities aren't, if the total probability isn't equal to 1 because I haven't normalized my wave function, I should also probably put that. However, most of the time it will be normalized, and so this denominator here is just 1. But anyways, for the case of an eigenstate of A, right, the expected value of A is just going to end up being and then A of psi was equal to a little a psi, and I can bring this constant A outside, and then this numerator and denominator will cancel. So the expected value is just this. Anyways, it's also useful to show that these eigenvalues are always real for a self-adjoint operator. And so if I consider psi a psi, I can either write this, I can write this as psi of a psi, and we said that a psi was equal to little a times psi, right? So I can bring out that little a as before, so it's little a times the inner product of psi with itself, which we could write as the modulus, sorry, the norm of psi squared if we wanted to. But anyways, since A is self-adjoint, we can bring it over to this side as well, and this inner product will be the same. And so, since this is equal to little a psi, using our sesquilinearity property, so that this first slot, I can pull out an a bar, we can get this expression. And so, as these two are equal, that means that A equals to A bar, and so the eigenvalues of a self-adjoint operator are going to be real numbers. Great. I guess it's time to actually look at some operators then. The first and probably the most straightforward one is just position, which is going to be equivalent to multiplying by x. Because if I've got a probability density function of x, then the expected value of x is given by this integral. We can then put our formula for the probability density function in, and then we can expand out as before. And so yeah, so the expected value of x is given by that as expected if we make the choice that the position operator, I'll write it as a hat just so it isn't as confusing, is essentially equal to multiplying by x. And so for the next operator, I would like to talk a bit about wave mechanics. And so we're going to assume that psi takes the form of a wave, it takes the form of a plane wave, which is going to be a complex oscillating wave. And so it's going to say psi of x is equal to e to the I kx minus omega t. We've got this negative here because if I move a wave forwards in time, right, so it might be here now, we can see that at a given position, let's pick this one for example, the point has moved down, and so it's sort of moved to the point which a point further backwards was, right? So this point here is moved to the height of. And so anyways, if we consider the derivative of this in space, so I'm going to write blah, which for one dimension is just going to be equal to the spatial derivative. So nabla of psi is going to be equal to I times k times psi. And anyways, this wave has a wavelength of 2 pi over k because e to the ix has a period of 2 pi, and so when we multiply by k, we're squashing it. And so that's equal to the wavelength, and so by the de Broglie relationship, P equals to h over lambda, and so the momentum is equal to hk over 2 pi. We're going to define the reduced Planck constant to be h over 2 pi, such that P is equal to h bar times k. And so to this expression, if we multiply both sides by negative I h bar, we're going to end up seeing that we're going to end up with h bar k of psi on this side, which we can replace with P. So this is one of those eigenequations. So this is an operator which we're doing to our ket, and then P here is the observable we're trying to measure, and it's just a constant we're multiplying by. Anyways, from this we can derive the kinetic energy operator, because kinetic energy is equal to P squared over 2m, and so that's equal to negative h bar squared over 2m multiplied by nabla squared. So this has now become a second derivative. And so with that, I can derive the Hamiltonian. This is going to be the kinetic plus the potential energy. And so this is going to be equal to negative h bar squared over 2m lambda squared plus b. And this, of course, is going to correspond to the eigenvalue of energy. So that's the observable I'm trying to measure. So the Schrodinger equation, h of psi is equal to E of psi. We can expand with this version of h, so negative h bar squared over 2m lambda squared of psi plus v. V is going to be a function of x, so I'm going to write it as v of x of psi is equal to E psi. Great. So this is a differential equation, and we'll solve it for some example functions of v of x in the next episode. For now, I want to look at E, because if I, instead of taking a derivative in space, took a derivative in time of psi, I would end up getting, just a reminder, this is psi, I would get negative I omega psi. So similarly, the time period of my wave is going to be 2 pi over omega, and so the frequency, which I'm going to write as nu, is going to be 1 over that, so it's omega over 2 pi, and so the energy, E equals to h nu, is going to give me h bar omega, and so I'm going to multiply my equation by I h bar, and so I'm going to get I h bar del over del t psi is equal to E of psi. I've now got two alternative forms for the energy. One is going to be about time, and one is going to be about space. And so depending on which derivative I can take, I can get different formula for energy. And so it's a reasonable idea to say that the time and space components of the Schrodinger equation are going to be independent, and so while psi might be a function of x and t, I can break it up into two functions, x of x and t of t. Just looking at this equation and substituting this in, the x of x is going to be a constant, so I can get pulled out of the derivative. But then I can divide by x of x, and solving this gives me t of t is equal to e to the negative I et over h bar. And the nice thing about this is the modulus of t is always going to be 1, right? And so while psi of x t is going to take this form and depend on time, if I consider my probability density function as the modulus of it squared, this is going to end up going away, and so for the case of my electronic structure calculations for a molecule, and most of the scenarios we're going to be looking at, we're going to neglect this time component and only consider this first time-independent component here. Anyways, there is one last thing to do with the Schrodinger equation, which is to derive the secular equation. And so if it happens to be that psi can be written as a linear combination in some basis n, then the Hamiltonian of psi using the fact that h is a linear transformation, I can put the h in here. And of course this is equal to E of psi based on the Schrodinger equation. And so I can pull this E out as it's just a constant, like this. If I then take an m, an arbitrary m from my basis set n, and then apply the bra of that to this, again it is linear, so I can bring it in. And then I get these inner product structures here. And so what I'm going to do to write this out neatly is I'm going to use a matrix, and I'm going to say HC is equal to ESC, where C is the vector of these Cn coefficients which make up my linear combination. H is going to have values equal to this inner product, that's row m and column n, and then S is just going to have the base inner product of m and n. The reason this works is because in my equation, if I write out, by iterating over n, I'm going down my vector c, I'm then going across, I'm going through the columns of my matrix H, and essentially what m is the row of my Hamiltonian I'm picking, because my product is going to be a vector, and so it's just going to tell me which of the items in my vector I'm going to get. So anyways, I have this equation here, and I can rearrange it to h minus es of c is equal to 0, and this is either going to have solutions when c equals to 0, or when my system of simultaneous equations, if you imagine this as a matrix times a vector equals to a vector, so this is a system of simultaneous equations, is either going to have solutions when my vector is 0 or when my matrix is singular, and so that's going to be the determinant of h minus es is equal to 0. Yeah, that's pretty much it for today. In the next episode, we'll go over some solutions to the Schrodinger equation, and then a bit later we'll come back to this secular determinant problem. Hope you enjoyed.